All right, so the title of this section, Shifting, Reflecting, and Stretching Graphs, really identifies the three key aspects of what we call transformations. Transformations, okay? We can shift, we can reflect, and we can stretch graphs.
Can we rotate?
Yeah, that takes a little different. So we have three main transformations. The first one we want to look at is shifting these. Okay, we can shift it either vertically or horizontally. And another name for this is what's known as translation. Okay, translation. Now, one important thing to understand about translations or shifts is that the actual graph itself is not going to change at all. It's simply going to move. And if you think, this parallels what we would think of when we're translating from one language to another. We don't want the meaning to change. We just want it to move from one language into another language. Okay? Everything else should stay the same. So when I have a function like this, and I want to simply translate it, I want it to look exactly like that. I just want it to be over here instead. Okay? That's a translation. It should look identical, just moved around. Alright? So we can translate things up and down. And to do this, yes?
Why do they translate things?
I'm sorry, what?
Like, why would they translate? Why would they want to shift it just like a couple things up or a couple down? Like, what's the reasoning?
Basically, so we don't have to do that part in our head. Like, if I were using a sine curve to model, like, the temperature in a room, you know, as the air conditioner kicks on and it cools off, then it turns off and it warms up gradually. You know, I could use a sine curve to model that. All right, but if we didn't have any kind of translations, I would have to have that centered at 0, and then I would have to mentally remember, okay, well, my thermostat's set at 75, so 0 really means 75. And then I'm having to do all these mental changes. Instead, I can just say, okay, well, it's my sine curve, and I'm just going to add 75 to it. Now the whole thing is shifted up. And I can look at the values and not have to do the mental changes.
Okay.
So here, if we want to shift upward, I'm going to actually use the example of f of x equals our parent function x cubed. If I want to move that up, say, 4 units, I can just take whatever f of x is, and I can add 4 to it. Notice I'm adding 4 to the entire function. Okay?
So would that be like saying f of x equals x cubed plus 4?
Yeah, it would be x cubed plus 4. I just take that function and I'm just adding 4 to it. Or if I wanted to shift it down, I would take whatever that original function is and I would just subtract 4 from it. So I have x cubed minus 4.
Now if it was already, say the function was f of x equals x cubed minus 2, and you had to do like a vertical shift upwards 4 units, you would just add 4 to the minus 2.
Yeah, it wouldn't have moved the parent function up 4, it would move the x squared minus 4 up 2, or up whatever.
Yeah.
Yeah, you can do this, you don't have to do this just with parent functions, you can do this with any function. If you add 4 to it, it's going to move that function up 4. Okay? Now, we also have horizontal shifts. And one thing to remember, both with the translations and with the stretching later on, the horizontal ones are the oddballs. They do the opposite of what you might think. Okay? If you want to move it right, Okay, you might think, oh, well, I just add to the x. You actually don't. If you want to move it right, you subtract from the x. If you want to move it left, you have to add. Okay, it's the opposite of what you might initially think. So if I want to shift x cubed 4 units to the right, I actually have to do f of x minus 4. Okay? So now we have an x minus 4 and that entire thing is cubed. Okay? It shifted it to the right 4 units. And basically by subtracting 4, what this does is it slows down when we reach where we would normally reach, okay? For example, x cubed normally hits 0 at 0. If we subtract 4, it slows our x down so we don't end up hitting 0 until over here at 4. And we typically hit 1 here at 1, but when we subtract 1, it slows the whole thing down so we don't end up hitting 1, this level, until we get all the way over here to 5. It slowed it down 4 units, okay? So the whole thing gets shifted over 4 units to the right, okay? On the other hand, if we were to add 4 to x, that's going to make us reach 0 faster. If I had x plus 4, I'm going to hit it 4 units earlier than I normally would. And I'm going to hit 1 4 units earlier than I normally would. And now we have the whole thing shifted to the left.
So the one you just did is the horizontal shift to the right? To the left.
Yeah, that's to the left, x plus 4. This one is a shift to the right, it's x minus 4. And that's cubed. This is just our parent function, x cubed. Okay? So, like we just saw, to shift it to the left, we would add, okay, to make it happen sooner. So x plus 4 cubed. So, those are our translations. Moving things around. We have these other two will actually change what the graph looks like. The reflections, okay, if you think about a reflection across the x-axis, all right, here's my x-axis. If I'm reflecting, it's only moving it vertically, or it's actually flipping it vertically. So the x's are all going to stay the same. All that changes is that all the y coordinates, our f of x, are made negative, are made the opposite. So here we would have a negative x cubed. Okay? To illustrate that, here's our x-axis. If I had this little triangle made from those 3 points and I reflect it across the x-axis, all the y-coordinates become negative, or they're opposites. So instead of a 2, 8, I have a 2, negative 8. And instead of a 5, negative 2, I have a 5, positive 2. And instead of 9, 6, it's now 9, negative 6. Okay? So everything has been flipped across this x-axis by simply making the y-coordinates their opposites. Okay? Now, similarly, if we want to reflect something across the y-axis, now the y's are not going to change. It's the x's that are going to be made their opposites. Okay? So it's f of negative x. And in this case, with x cubed, back to my pen, with x cubed, I would have a negative x being cubed. Okay? So notice here the entire function is being made negative. Here just the x is being made negative.
Why wouldn't the cubed go inside the parentheses?
On this one?
No, the y-axis one. Yeah,
Because it's altering the x, not the entire function itself.
Yeah, that's right. We're multiplying the x by a negative 1, not the entire function by a negative 1.
So,
Okay.
like for the reflection across the y-axis, the y could, like, the x could still, get it, like, because if you, like, did, like, say it was, like, negative 2 cubed, that would be a positive 8, wouldn't it?
Negative 2 cubed would be a negative 8. Now, this one's a little bit strange because actually if you simplify both of these, they'll give you the same thing. And that's because x cubed is what's known as an odd function, which we'll talk about later. But just for now, recognize the difference between multiplying the whole function by a negative and just the x by a negative. Here you're actually substituting in, if this were an x cubed plus 3x squared plus 4x, everywhere you saw an x, you'd plug in a negative x.
And then if it was the one where you have to change the whole function to negative, it would like be negative 4x.
Yeah, you would just distribute a negative to every term in that function.
So if it's x-axis, we're dealing with the whole function, like we add negatives to the whole function, but if it's y-axis, it's just to x.
Yes.
It's just like flip, right?
Yes.
Like,
Yeah, and actually you can see that here. If I put this up, to reflect it across the y-axis, this 2/8 is now a negative 2/8. The 9/6 is now a negative 9/6. The 5 negative 2 is now a negative 5 negative 2. Okay? All the x coordinates were made their opposites. Okay? Alright, one last one I'll show you. We'll touch on this more tomorrow when we talk about this a little bit. And that is across the line y equals x. This has significance because this is actually how you can find an inverse function. Okay? An inverse function is where we basically swap all the x and y coordinates. So instead of 9/6, it's 6/9. Instead of 8/2, instead of 2/8, it's 8/2. Instead of 5 negative 2, it's negative 2/5. Okay, so you have all of those switched. That's what makes it a reflection across the line y equals x. Okay? The last little thing here, not sure if we have 2 minutes or 4 minutes, but
We have 2.
okay, so we have 2 minutes, that's good. The last little thing here is the stretching or shrinking, okay? And the stretching or shrinking, again, the horizontal one is kind of the goofy one. The vertical one is nice and easy. If you're multiplying by something bigger than 1, it's going to stretch it vertically. So if you have 2f of x, that means all your y coordinates are going to be doubled. If you have 5f of x, it means all your y coordinates are going to be multiplied by 5. Okay? However, if you multiply by a fraction, it's going to shrink it vertically. Okay? So if you multiply by a half, the whole thing is going to be half as tall. Alright? Horizontal works the opposite way.
are we going to talk about
So where are the reasons?
Yeah, we'll finish that up a little bit tomorrow.
No.
Yeah.
No, you're not.